Hi, my name is Abdurrahman from Maple Systems, and I'll be going over the 2's complement and double words 2's complement ladder instruction in this video tutorial. First, let's hover over the conversion tab and place the 2's complement instruction on the first rung. Now let's go back and place the double word 2's complement on the second rung. Now that we know where the instruction is and what it looks like, let's go over to screen number 4 and place the appropriate ladder logic subroutine on the right hand side of the screen. According to the logic subroutine, when the coil B400 turns on with a push of this button here, the 2's complement ladder instruction executes and the 2's complement of operand A will be stored in operand B. The double word 2's complement works exactly the same way, except that we have allocated additional memory to accommodate for an extra word. On screen number 4 we have two rows. The top row is a single word 2's complement, where the minimum and maximum sign values are negative 32,767 and positive 32,767. Within the first column we have operand A's binary and decimal data types. Both types are addressed to the same register, D410, but they are displayed in two different forms, binary and decimal. When we input a decimal value for operand A, the appropriate binary value will be displayed on the left. When we press the convert button, the instruction will apply 2's complement on operand A and place the result in operand B. The same is true for the bottom operands, except that we have allocated memory for a double word rather than a single word. We have allocated 4 bytes instead of 2. And that is apparent when we pull up the edit tag window. The 4 bytes which is allocated on the bottom represents a double word memory allocation, which means that the minimum signed value for a double word is negative 2,147,483,648, and the maximum value is the absolute value of the minimum. So how is this actually determined? Well, there are 8 bits in each byte, which means that 4 bytes has a total of 32 bits. So let's pull up our calculator and turn on the first 32 bits and see what the decimal value comes up. So this number isn't what we expected, and that's simply because we are dealing with signed numbers on the HMC. We have to take consideration of the negative values as well. So let's divide the number we see on the screen by 2, so the half the number range would be considered positive and the other half negative. And now we see a number that we recognize. Simple as that. Now let's review how 2's complement work. 2's complement is used when determining the negative value of a certain signed number. So if I have a signed number 256, a 2's operation will output the value negative 256 in binary form. So let's take the 2's complement of the number 484. The binary representation of 484 is 0001 1110 0100. The first step we'll need to take is to invert each bit in the binary. So 0001 1110 0100 inverted is 1110 0001 1011. The second step is adding a 1 in the least significant bit and carry a 1 if the sum of the value is 2. So starting from the least significant bit, or LSB, 1 plus 1 equals 2. So let's carry a 1 and insert a 0 in the LSB placeholder. Now we are looking at this bit. Again, it's 1 plus 1 equals 2. So let's carry a 1 and insert a 0 in the placeholder. For the next bit, which is to the left, let's add. So 1 plus 0 equals 1. So we'll need to insert 1 in the placeholder. Since there aren't any more bits to add, we can drop down all the bits to the left. The result is 1110 0001 1100. We can confirm this result by pulling up our handy dandy calculator and typing in the signed decimal value of -484 and converting it into binary. As you can see, the binary equivalent of -484 on the calculator is the same as we did by hand. Let's review this instruction on the HMC. On the HMC, let's enter a number for operand A. When we have entered a number, notice that the binary number has been changed accordingly. Now let's press the appropriate convert button and see what happens. Observe that the 2's complement operation has been applied, which means that operand A's binary value has been inverted and a 1 has been added to the least significant bit. After summing up the binary number, the 2's complement is placed in operand B. Observe. Now the same is true for our double word 2's complement. Let's do a test example on the double words 2's complement and see what happens. And that concludes our video tutorial for the 2's complement and double word 2's complement ladder instruction. If you have any questions, please call Maple Systems or visit us online at maplesystems.com.